This lesson is about combining functions. Before doing this lesson, you should already be familiar with what we mean by a function and also what we mean by the domain and range of a function. In this lesson, we're going to look at different operations that we can use with functions. The first of these operations are algebraic operations that will combine functions to create new functions. Now, these algebraic operations operate very much like you would expect them to, so I don't expect you to have too much difficulty with this concept as far as doing the actual combining of the functions. Perhaps the hardest part of this might be in thinking about the domain of these new functions that we have created. The other operation that we will talk about in the latter part of this lesson is called composition of functions. That operation is a little bit different than any type of operation you have seen in algebra, so I would ask you to pay particular attention to that operation when we get to that particular part of this lesson. Let's look at some of the rules for the algebraic operations involved in combining functions. Combining functions using algebra. Let f and g be two functions with domains a and b. Then we can define the following with domain A intersect B. Now let me talk about this before we go on. You may or may not be familiar with the set notation that we've used here. This intersection symbol is another way of saying what two sets have in common. So what we're saying here is if we have one set of numbers that is the domain of function f and another set of numbers that is the domain of function g, then we will take only those numbers that appear in both A and B at the same time, those numbers that are common to A and B. So if they're numbers that are in A but not B, those will not be included in the domain of our new function. Now, our first operation is the addition of functions. I want you to pay attention to the symbolism that we use here. Notice in parentheses we have f plus g. Now, f plus g is indicating that we're adding the two functions f and g. Now, after we have this f plus g in parentheses, we have another parenthesis with x. Now, this is operating much like we have seen f of x in the past. In other words, this x is simply identifying our independent variable, or if you will, the argument of this function f plus g. So here's the name of our function f plus g. This is the argument of our function. Now, in order to get this function that we call f plus g, it's simply a matter of taking the function f of x and adding the function g of x. And you will see when we get to the examples, we will add these two functions exactly the way that you would think that you would do that in terms of combining like terms. Our second function is the difference of two functions. And again, notice the notation. The function that we're going to name f subtract g, or f minus g, of x, again, x is our independent or domain variable. This difference function f minus g is found by taking the function f of x and subtracting the function g of x. Again, this operation will operate much like you expect it to. I will caution you to be careful with signs, which is always a problem when you're doing subtraction. Our third function is the product function. We have the function, notice fg here. Recall anytime in algebra when we write two things side by side like this with no operation symbol, we're indicating the multiplication operation. So this is indicating the product of the two functions f and g. Again, x is our domain or independent variable. So this is read fg of x. And notice what we do here. F of x, our function f of x, is being multiplied times our function g of x. And again, this operation will be like you expect it to be. Our fourth operation is the quotient or division. The quotient f over g of x is found by taking the function f of x and dividing by the function g of x. Now you will notice on this fourth one, there is an extra condition. Not only do we have to follow this domain being those numbers that are common to both sets A and B, but we also have to be careful that this function g of x here in the denominator never becomes 0. We don't want to, of course, have an undefined situation here, so we do not want this denominator becoming 0. So that means we will eliminate from consideration of our domain any value of x that would make this denominator become 0. Okay, well let's look now at some examples where we're going to perform these operations. Notice we are to find f plus g, f minus g, f times g, and f divided by g, and we're also asked to give their domains. Okay? Now here's function f of x, 3x squared plus 5x minus 2, and function g of x is 4x plus 3. Okay? Now, I think what I want to do here first is let's just go through the operations. So remember our notation. We're going to put a parenthesis, f plus g, and then in our second parenthesis, x for the argument of our function. So f plus g of x is going to equal, and if you recall in our definition, all we're going to do over here is take the function f of x and add the function g of x. So let's write down what f of x is. F of x is 3x squared plus 5x minus 2. So there's f of x. We're going to add to that g of x. Well, g of x is 4x plus 3. Now, if you want to, for emphasis here, you could, of course, parenthesis f of x. Let me put that in. And g of x. And show that you're taking f of x and you're adding g of x. Of course, when you're adding, it isn't necessary to put those parentheses in because when you eliminate parentheses, none of the signs would change. So let's just look at this and do the addition. Looking at our first term, 3x squared, there are no other like terms, so we'll just bring that down. But notice we have the like terms 5x here, and we're adding 4x, so we'll add those together. 5x plus 4x is 9x. And then our like constants, negative 2 plus 3 will be a positive 1. So that's all that's involved in terms of doing the addition of the function itself. Okay? Now, let's go ahead and do the difference function. So in parentheses, f minus g. Again, of x, you want to put that notation down because this is a function. We will take function f, again, 3x squared plus 5x minus 2. And again, if you want to parenthesis that, you may. You don't have to, that first one. But it will be necessary because of our subtraction here to parenthesis our second function, g of x. We're taking f of x, we're subtracting g of x. And of course the necessity for the parentheses is because what do we need to do with this negative? We need to distribute it, don't we, to both of these terms. So I'll take one more step here. We have 3x squared plus 5x minus 2. Removing our parenthesis, we have a minus 4x minus 3. Now we will combine our like terms again. 3x squared will be brought down. 5x minus 4x gives us a positive 1x, and negative 2 minus 3 gives us a negative 5. And so this will be our new function that we call f minus g of x. Okay, see, these operations are not difficult. They're doing exactly what we would expect from algebra, aren't they? Okay, let's go to our product function. F times g of x. Again, notice we want that f times g in parentheses for our notation. So we're going to take function f of x, which is 3x squared plus 5x minus 2, and we're going to multiply. So let's do our second parenthesis right beside that to indicate multiplication. We're going to multiply that by 4x plus 3. And now we're going to carry out this multiplication. Since we're multiplying a trinomial times a binomial, what I'm going to do is take my 3x squared and multiply times both of these first. So 3x squared times 4x gives me 12x cubed. And then 3x squared times our positive 3 gives us a positive 9x squared. Okay? Now we'll pick up our 5x and multiply it times both of these terms. So 5x times 4x gives us a positive 20x, and 5x times a positive 3 is a positive 15x. Oh, I'm sorry, I forgot an x squared, I think, here. 5x times 4x is 20x squared. Let me get that on there correctly before we move on. And then finally we will pick up our negative 2. Negative 2 times 4x is a negative 8x. And negative 2 times a positive 3 is a negative 6. Okay? So does everybody follow the steps that we went through to pick up each of these terms that we have here? Okay? Now let's combine our like terms. I have 12x cubed. Let's see, we can add our 9 and our 20x squared, so we have a positive 29x squared. And 15x minus 8x is a positive 7x. And then bring down our minus 6. So again, a very simple procedure here in terms of doing these operations, aren't they? We have one other operation to do, and that is the quotient. Let me just slide a paper up here so you can see that. We're going to do the quotient f over g of x. And to do the quotient, we take the function on top, which is f of x. So we're going to write 3x squared plus 5x minus 2. And we're going to divide that, so we'll use our fraction bar for division. Our function g of x, which is 4x plus 3. Okay? Now, we might want to determine whether we can reduce this new function that we have created or not. I notice that I can factor my numerator. Let's see, it would have to be 3x times 1x. To get that 5 in the middle, I'll need this configuration. I believe it's 3x minus 1 times x plus 2, isn't it? 3x squared, 6 minus 1 is our 5x minus 2. Now you'll notice I wanted to factor to see if I could reduce this a little bit, but it does not reduce, does it? So we could leave this, in fact, in this form right here. So again, the operations themselves are not difficult. But let's talk about domain, okay, now that we've done the operations. You'll recall in our definitions here, when we're combining these functions, we need to know what the domain of function f is. We need to know what the domain of function g is. And then what we need to do is find out what they have in common. Well, for this first example that we've done, it's really not going to be too difficult because I chose functions that are real simple. What do you know about the domain of function f here? What kind of numbers can you use for x? Well, you can use any number you want to, can't you? So the domain of function f is all real numbers, isn't it? What about function g? What kind of numbers can you use for x in function g? Again, you can use any number you want to, can't you? So the domain of function g is also all real numbers. So it turns out for these functions, they have exactly the same domain to begin with. So when we add, subtract, and multiply, the numbers that are common to our two domains is, again, all real numbers. So the domain for the sum is all reals, the domain for the difference is all reals, and the domain for the product is all real numbers. Now, when we get to our quotient, though, we have to make a slight modification. And the reason is, I have to be careful about my denominator. Recall that when you do the quotient, let me remind you again what has to be true. Our denominator cannot become 0. Well, what we want to look at then is look at our denominator, 4x plus 3. Can 4x plus 3 ever become 0? Can it ever equal 0? Well, certainly it can, can't it? If we solve this for x, we find out that if x is negative 3/4, then we would get a 0 in our denominator, wouldn't we? So what we want to say here for our domain is the real numbers, but we want to take away negative 3/4. Now, one way that you can say that is to say the reals minus, meaning take away or leave out, the number negative 3/4. Another way, of course, that you could write this domain with our interval notation is to say that from negative infinity, we can go all the way to negative 3/4, use a parenthesis, and then we could pick up on the other side of negative 3/4 and go to positive infinity. So that would be writing the domain with interval notation. Another popular way of saying the domain is simply to say x cannot be negative 3/4. So this is 3 different ways that you could indicate the domain of this quotient function. Now, I hope that what you've seen in this first example, first of all, is that the operations themselves are pretty simple. They do exactly what we expect from the things that we know about algebra in the past. And so as we look at this second example, let's keep that in mind. Again, we're asked for the sum, difference, product, and quotient. And again, we want domains. So I think I'll do this the same way. Let's run through the operations themselves, and then let's talk about the domains here. Okay? So let's start with our function f plus g of x. That means I want the function f of x, which is the square root of x minus 5. And I'm going to add to that the function g of x, which is the square root of x minus 12. Now, this is real simple. I'm finished. And the reason, of course, that I'm finished is when you have radicals and you're adding, you can only add them if they're alike, sort of like variables. These two radicals are different, so I can't combine them in any way, and that's the only way that I can indicate this sum of my two functions. The difference, f minus g of x, means that we take function f again, square root x minus 5, but this time we're going to subtract function g, which is the square root of x minus 12. Now again, there's nothing else that I can do in terms of simplifying the way this function looks. When I'm subtracting radicals, they have to be alike to subtract them. And remember, a negative in front of a radical like this cannot be distributed across like it can with a parenthesis. So again, that's all I can do in terms of this operation. Our third operation, the product fg of x, means that we take the square root of x minus 5 and we multiply it times the square root of x minus 12. Now here we can do something different. Remember, we had a rule that says the square root of a times the square root of b is equal to the square root of a times b. So I can make this one square root where I multiply the x minus 5 times the x minus 12. And then you may want to actually do the FOIL here to write this out. X times x is x squared. I have a minus 12x and a minus 5x for minus 17x. And a negative times a negative gives me a positive 60 here. And so we might want to write this third function in this form here. So in this case, I can do something else to simplify because I can multiply radicals together. Our fourth operation, of course, again, is the quotient f over g of x. So we have the square root of x minus 5 divided by the square root of x minus 12. Now on this one you really have a choice. You could leave this like this if you want to, or because of our rules of radicals, we could write a single radical where we put the fraction x minus 5 over x minus 12 underneath that radical. On this one, I would encourage you to do the multiplication. Here, it really doesn't matter whether you leave it in this form or this one. Either one would be considered an okay form for this solution. Now, our work on this problem is going to be a little bit more complicated in terms of finding the domain than what our last example was. So I want us to take a look here, first of all, at function f. Now recall, when you have a square root, this is not defined if what's underneath here becomes negative, is it? So for function f, x minus 5 has to be greater than or equal 0. It has to be positive or perhaps equal to 0, which says x has to be greater than or equal 5, doesn't it? So I'm going to make a note up here for the domain of function f. X is greater than or equal 5. Recall, if you prefer the interval notation, that would be a bracket from 5 to infinity. You may write that either way that you choose. Now for function g, again we have a radical and we can't get a negative under there, so on this one x minus 12 must be greater than or equal 0, which says x must be greater than or equal 12. Alright, for function g then, x must be greater than or equal 12. In the interval notation, that means from 12 to infinity, like that. Now, having written those domains for functions f and g up there, let's talk a little bit about what we want to do. We're trying to find what's common with these two sets. Here we have numbers larger than or equal 5. Here we have numbers larger than or equal 12, don't we? Let's think about a number line for a second. If I take a number line, and here's 0, and let's say 5, the numbers greater than or equal 5 would be from 5 to the right, like that, wouldn't they? Let's do a second number line right underneath there. Here's 0, here's 5, and 12, of course, is over here somewhere. The numbers that are greater than or equal 12 would be from 12 to the right. Now, what numbers do these have in common? Do you see that it would be only the numbers greater than or equal 12? Only these numbers. These numbers between 5 and 12 are in the first set, but they're not in the second set. And of course, these numbers down here are not in either set. So the numbers that are common are those values of x greater than or equal 12. So for f plus g, our domain is going to be x is greater than or equal 12. For f minus g, domain x is greater than or equal 12. For the product, domain x is greater than or equal 12. Now, what about this quotient? Is anything going to be different for our quotient? Well, notice we still have to keep this positive, but we also, in this case, have to not let this become 0. What value would make this become 0? 12 would, wouldn't it? So x can't be 12, otherwise this is undefined. So what we'll do on our domain is refine it just a little bit and say x has to be strictly greater than 12. We're going to remove the or equal part from the domain since we cannot use 12 in that quotient. Okay, I have one other example here where we're going to do some algebraic operations, and this may take us a little bit longer as far as the operations are concerned because of the fractions that we have here. Now, I think what I'd like to do here first is let's go ahead and talk about domain since we have fractions. Notice on this first fraction, we have to be careful. X can't be what number? It can't be 2, can it? So I'm just going to make a note up here that x cannot be 2. It can be any number except 2. Is that correct? Okay, what about g? On g, x cannot be negative 3, can it? Okay, otherwise those are undefined. Now, when we start our operations, and we're going to do f plus g of x first, we take function f, 4 over x minus 2. We're going to add function g, which is 5 over x plus 3. Now, I think you can see immediately right here, not only can x not be 2, but it also cannot be what? Negative 3. So I'm going to go ahead and make a note on our domain. X cannot equal 2 or negative 3. All other numbers would be common to the domain, wouldn't they? Now, we're going to do some algebra here. We need a common denominator. Since we can't factor x minus 2 or x plus 3, either one, we consider those factors. And our common denominator will be the product x minus 2 times x plus 3. Okay? Now, on this first fraction, we need to multiply that first fraction in numerator and denominator by what? X plus 3. So our 4 is going to be multiplied by x plus 3, isn't it? Okay? For our second fraction, again, our common denominator, x minus 2 times x plus 3. This second fraction needs to have the numerator and denominator multiplied by what? The x minus 2, doesn't it? So 5 times x minus 2 here. Okay, let's do our work then. We have 4x plus 12, and since we're adding, I'm going to go ahead and put plus the 5x minus 10. All of this is over our common denominator, x minus 2 times x plus 3. And then combining our like terms, 4x plus 5x is 9x. 12 minus 10 is a positive 2, so we have 9x plus 2 over x minus 2 times x plus 3. Okay? So again, the operation, although it's more difficult, follows exactly what we expect, doesn't it, in terms of doing that addition. Now, keep in mind for our difference function, f minus g of x, we take our fraction 4 over x minus 2 and we do what? We subtract 5 over x plus 3. Now we can save just a little bit of work on this second one since we've already done our addition, because we know again our common denominator is going to be this x minus 2 times x plus 3. And we know what? That our first fraction is going to be multiplied by the x plus 3. So I'm going to have 4 times the x plus 3. The difference is I'm going to be subtracting the 5 times the x minus 2. This second fraction again is going to be multiplied by x minus 2, but that's going to be a subtract sign. So I'm just going to save us a step here by doing that together right there. Now when we distribute this, we have 4x plus 12, be careful with your signs, minus 5x plus 10. Again, this is over our common denominator, x minus 2 times x plus 3. Now, let's combine our like terms and simplify here. 4x minus 5x is a negative 1x, and 12 plus 10 is a positive 22. Again, this is over our common denominator of x minus 2 times x plus 3. Let me slide that up. I didn't realize that was off the screen there. 4x minus 5x is our negative 1x. 12 plus 10 is our positive 22 over our common denominator. And again, we've already calculated the domain when we did it for the sum. X can't be 2 and it can't be negative 3, can it? Okay? Now, our third operation is going to be our product function, fg of x. So we have 4 over x minus 2 being multiplied times 5 over x plus 3. And again, we have the same domain here. X can't be 2, can't be negative 3, can it? Okay? Now, let's look at our product here. When we multiply fractions, recall we just multiply numerators together, so 4 times 5 is 20. And we multiply denominators. Now here, I'm just going to leave this in factored form because we usually do that with our rational type functions. You could, of course, do FOIL here and multiply this out if you wanted to, but this is an okay form to leave this product of our two functions. Okay, our last operation is to do our quotient, f over g of x. So we take our function f, 4 over x minus 2. We divide that by 5 over x plus 3, don't we? Okay? Now, notice that we still can't have x being either 2 or negative 3, or one of these things would be undefined, wouldn't they? Is there any additional restriction that we would have in looking at this? Is there any other number that would make this denominator become 0? 5 over x plus 3 will not be 0 because the 5 will not ever be 0. So this fraction will not ever be equal to 0, will it? So all we need to do here is to simplify our fraction, and recall this complex fraction just means 4 over x minus 2 is being divided by 5 over x plus 3. And so when we invert, we have 4 over x minus 2 times x plus 3 over the 5. And then if you want to do this multiplication, that's 4x plus 12 over 5x minus 10. You could, of course, if you want to, leave this as 4 times the quantity x plus 3 and 5 times the quantity x minus 2. Either of these would be a good form to leave this. Now our domain, x still can't be 2 and it can't be negative 3. If you look at this final form here, it appears that the only restriction would be that x could not be 2, doesn't it? But you'll notice in the original definition, if we're going to combine these, we start out by the numbers that are common to a and b, And since we could not use the -3 for that second function, we still can't use it to do the quotient because we can't be dividing by a function that's undefined in the first place. Now, in our next example, we're still going to be looking at addition of functions, but we're going to be looking at it from a graphing standpoint. Notice it says to use graphical addition to graph f plus g. Now, to understand what we're going to do on this graphical problem, I want to go back again and look at this combining functions definition for just a second. Notice when we add the functions f and g, we're adding f of x and g of x. Recall that this symbol f of x is a replacement symbol for what variable when you use the variables x and y? It's a replacement for y, isn't it? F of x means the value of the function at x, or the value you get when you substitute a certain value into x. And so that's a replacement for the y value, isn't it? So this is the y value for function f, this is the y value for function g for a particular x value. So what we're going to look at here, this is function f, and this is function g down here, and we're going to add these functions, and the way we're going to add them is by thinking about what are the y values of these functions. Okay? Now what I'm going to do are to pick some specific points that I can read exactly off the graph. For instance, right here, I can read exactly what the y values of those two functions are. Now let's get our x value. 1, 2, 3, 4, 5. That's at x equals -5. Okay? At x equals -5, the y value on function f is 2, and the y value on function g is 1. So I'm going to add those. 2 plus 1 gives me a what? It gives me 3, doesn't it? So over here, at x equals -5, I'm going to go up to 1, 2, 3. And I'm going to plot that point. Okay? Now let's find another place. Right here. Do you see these two values? This is at x equals -3. Notice function f has a y value of what? 4? But function g has a y value of 0. What do you get when you add 4 and 0? You get 4, don't you? So whenever x is -3, y is 4. That will be right in there. Okay? Now another point that I can see specifically is right here. At x equals -1, this y value is 3. This y value is -1. What happens when you add 3 and -1? Well, 3 and -1 gives us a what? It gives us a 2, doesn't it? So at x equals -1, I have a 2. Okay? Notice here, at x equals 0, we can get pretty close on that one. My y value here is a 2. My y value here looks like -1.5, doesn't it? What's 2 minus 1.5? It's about a 1/2, isn't it? So I'm going to put a point right there. Okay? Do you sort of get the idea of what we're doing? We're adding y values. Now I'm going to show you something else that you can do here in a minute. Right here I have at x equals 1 a y value of 3 for function f and a y value of -2 for function g. Well, 3 plus a -2 is what? 1. So at x equals 1 I have y equals 1, don't I? Okay? Let's get this point right here. Let's see, that's not going to be exact, but we can get close. 1, 2, 3, 4, 5. Y is 5 there, and -2.5, let's say here. Well, 5 minus 2.5 is 2.5, isn't it? So at x equals 2, I'm about 2.5 right there. Okay? Let's see. It looks like I can pick up these exact values here. 1, 2, 3, 4. That's at x equals +5. 1, 2, 3, 4, 5, 6, and minus 1, 2, 3, 4. So 6 and a -4 added together gives me a 2. So at x equals 5, I have a 2. Now you'll see these points, and we can sort of connect those and get an idea of what this function looks like, can't we? Okay? Now, we could get more points in between these and get a better sketch, but that would give you some idea of what the function f plus g looks like, wouldn't it? Now, another way that you can sort of do this without actually adding the coordinates is to think about doing something like this. With a ruler or something, you can measure from your x-axis the distance up to that y value on this function down here, and then take that up to this other function and add that on there. And you'll notice that would put your point right here. That would correspond to this point that I have right here, wouldn't it? Okay? Notice that you're adding smaller amounts here until here you're adding a 0. So you can see that this is going to increase till it gets to right up about there. And then notice this function becomes negative for the y values. That means these points are going to be lower, aren't they, than what these points were right here. And so you can see that this graph is going to come down below something like that, which we see over here. Okay? So the idea again is that when you're adding functions f and g, to keep in mind you're adding their y values. So if you have a graph of two functions, then you can pick certain points where you can read off the y values of the two functions, add those y values together, and that gives you a point to plot over here for the graph of f plus g. Okay? Now at this point we have had a pretty good sampling of our algebra operations for functions, addition, subtraction, multiplication, and division. So now we want to turn our attention to that other operation that I mentioned to you earlier called the composition of functions. Now this is going to look a little bit different for you, and you're going to need to just understand what the notation is telling you to do to understand how to do a composition. Composition of functions. Given two functions f and g, the composite function, sometimes we read that f circle g, just like it looks. Another way to read that is f composed with g. Now this is probably the more technically correct way to say it, but we get lazy and it's just so easy to say f circle g, so you'll hear me saying that a lot, meaning the composition. So f circle g, the composition, f composed with g, is defined by. Now you'll notice here, just like before with our plus, minus, so forth, this is just indicating our function operation. F composed with g of x, or f circle g of x. So this is our function notation. Now over here it tells us how to get that function. Now keep in mind these layers of parentheses. Do you see your f here and the parenthesis here? We read this f of, and in here we have what? G of x. F of g of x. Now the thing to notice here is that g of x is the argument of function f. Or in other words, g of x is what we're going to replace our independent variable with in function f. Okay? So what we're doing here really is we're placing one function inside of another function, if you will. Okay? Now, the domain consists of those elements in the domain of g for which g of x is in the domain of f. Now this will be a little bit more clear when we look at some of our examples, but what we're saying here is we have to start out with those numbers for which g is defined. Okay? G has to be defined first. And then the result of putting that x into function g goes into function f, so that result, g of x, has to be in the domain of function f. Now, first of all, I want us to concentrate mainly on this definition. How do we actually do the algebra, so to speak, to get the composition function, and then we're going to talk about that domain situation. Find f circle g and its domain. Okay? Now, before we get started with the composition, let's just go ahead and make a note here for f of x. What is our domain for function f? X can't be what? It can't be 3, can it? Okay? What about function g? Are there any restrictions on function g? There are none, are there? In function g, we can use any number that we want to. Okay? Now, I want to look at notation first. F circle g in parentheses of x. F circle g of x is given by, I'm going to write the definition, it said f on the outside, it had a parenthesis, and then it had g of x on the inside. Okay? Now, a lot of times, here's what I like to do. I'm going to start on the inside, just like we normally do, and I'm going to replace g of x with what it's equal to. Okay? What is g of x equal to? G of x is x minus 5. Okay? So notice what I've done here. I've put in place of g of x what g of x is equal to on that inside part. Now, this becomes a little bit more familiar notation. This is saying go to function f and replace the variable, the independent variable in function f, with x minus 5. So looking at function f here, I'm going to replace this variable right here with x minus 5. So for emphasis, I'm going to put that in a parenthesis. I'm putting x minus 5 in place of x. Notice then I have a plus 2. And then going to the denominator, in place of this x, again I put x minus 5. And then I subtract 3. Now take a look at what we've done here. You've got to understand the proper way to do this. Notice here, f circle g, this function f that's on the outside, so to speak, here is on the outside here. So that stays in that order. This g becomes the inside function. Okay? Our first step is to replace the inside function with what it's equal to. And then we go to our other function, our outside function, and we replace this quantity here in place of our variable in this outside function. Now, let's do some simplifying. X minus 5 plus 2, of course, is x minus 3. And x minus 5 minus 3 is x minus 8. Okay? Now, I want to talk a little bit about this domain idea. The domain, let's go back and look at this, consists of those elements in the domain of g. So you start out thinking about the domain of your g function, your inside function, for which g of x is in the domain of f. Okay? Now, let me show you what happens with this example. It's obvious in this final simplified form that x cannot equal 8, can it? Okay? Well, let's see what happens if we let x be 8 in function g. 8 minus 5 gives me what? 3. Notice 3 is not in the domain of function f. X can't be 8 because if x is 8, I get a 3 which can't be put into function f. Now, a lot of times I suggest to students that they kind of wait until after they've done the composition function, and then perhaps it'll be a little bit easier to determine what the domain of our new function would be. Okay, let's look at this one. Find f circle g and its domain. And again, we're given f of x and g of x. Now here, our domain for function f is any real number, isn't it? We can put anything we want to in there. What is our domain for function g? What do we have to be careful of? This can't become negative, can it? So x minus 2 must be greater than or equal 0, which says x must be greater than or equal 2. We do have a restriction on function g. I'll come back to these domains in a little bit. Let's do our f circle g thing. F circle g of x, remember f is on the outside, g of x goes on the inside here. Now the first step is to replace this g of x function. So f of, in place of g of x is the square root of x minus 2, isn't it? Okay? So this means what? We're going to look now at function f right here, and we're going to replace each of these variables with this square root. So I have 2 times the square root of x minus 2, that has to be squared, notice, minus 3 in place of x, the square root of x minus 2, and then plus 1. Now we can do a little simplifying here. If I square this radical, what happens to that radical? It disappears, doesn't it? So I have 2 times x minus 2 minus 3 times the square root of x minus 2 plus 1. Distributing, I have 2x minus 4 minus 3 times the square root of x minus 2 plus 1. And let's combine those like terms. 2x, I'm going to go ahead and bring down the minus 3 times the square root of x minus 2 here. Negative 4 plus 1 is a negative 3. Now, looking at this new composition function that we have, do you see a problem with any particular value of x that we might not be able to use? Look at this term right here. We still have that radical, don't we? So it's still obvious here that x cannot be less than 2, can it? So x has to be greater than or equal to here for the domain. We can see that from this. I want you to notice, though, also, if you go back to your definition again, the domain consists of those elements, what? In the domain of G. So we would have started with the domain of G and then just worried about are the results in F. Since we can put anything in F, all we have to worry about is what was the restriction on G. And you'll notice that shows up right down there again. Okay, now on this example, we have a little bit different problem. Find F circle G of 3. Instead of x, it says 3. Now you'll notice here we have f of x and g of x. Here we have 3. Now I want to show you two different ways that you can do this problem. First of all, you might want to start out and just say, okay, well, I'm just going to find f circle g of x like we've been doing. F of g of x here. So replacing g first, in place of g I have 2x minus 7 here. And then this tells me what? Go to function f right here and replace my variable with 2x minus 7. So that would give me 5 times 2x minus 7 and then plus 4, wouldn't it? Distributing, I have 10x minus 35 plus 4, or 10x minus, oops, I missubtracted, that's a 31 there. 4 from 35 is 31. So 10x minus 31. Let me rewrite that. 10x minus 31. Now, if I want f circle g of 3, since I have a definition, I can just replace this with a 3. 10 times 3 minus 31 is 30 minus 31, or negative 1, isn't it? That's one way. Now, I would recommend this one way if you're going to be evaluating f circle g at lots of values. But here's another way you can look at this thing. F circle g of 3 could mean f of g of 3, just like f circle g of x means f of g of x. Now, let's come down here. What is g of 3? Well, that means what? We're going to put a 3 where x is here, so 2 times 3 is 6. Minus 7. 6 minus 7 is what? Negative 1. Okay, so we're going to replace g of 3 with negative 1. Now this says go to function f right here and replace the x with negative 1. So if I do that, 5 times negative 1 is a negative 5. Negative 5 plus 4 is negative 1. You'll see this answer is exactly the same as this one. Now, I'll point out this was a coincidence right there, so that's not always going to be that same answer. This was a little bit quicker and easier, wasn't it? If you're only going to evaluate the composition of two functions at one value of x, this would be probably the easiest way to do that. But as I said before, if you're going to be evaluating for lots of values of x, like what if you also wanted to know what is f circle g of 2, and what is f circle g of 1, and so on, then it would be better to do the general form first, and then you could just substitute those numbers into that general form and get as many values as you wanted to. Okay? Now, in our next example, we're asked to find several things. Notice it says find f circle g, find g circle f, find f circle f, and find g circle g. Now, don't let these differences bother you. We're going to stick to that same general plan. Let's start, and we've done these before, with our f circle g. F circle g of x, remember the function that's here on the outside stays on the outside. F of g of x, like we've done before. Now, what do I replace first? This inside function, don't I? So f of, what goes in place of g of x? 3x minus 1 does, doesn't it? Okay, now this tells me now look at function f right up here and replace our x with 3x minus 1. So I'll have a 3x minus 1 squared plus 2 times 3x minus 1. Now let's simplify. If I square this binomial, I have 9x squared minus 3x doubled is a minus 6x, and then plus 1. And distributing, I have a plus 6x minus 2. Combining our like terms, 9x squared. Notice our minus 6x and plus 6x is going to drop out. 1 minus 2 is a negative 1. So F circle G of x gives us 9x squared minus 1. Okay, now that's what we've been doing. Now notice he turns that in a different order and says find G circle F. Well, let's take a look at what happens when we do G circle F. Notice this time my function G is on the outside, so it's going to stay on the outside. And this time F of x will be on the inside. G of F of x. Okay, now which one do I replace first? I replace the inside one first. So let's leave G. We're going to replace F with what it's equal to, which is x squared plus 2x. Now this says go to function G, look at G right up here, and replace our x with x squared plus 2x. So 3 times x squared plus 2x, and then minus 1. Let's simplify. We have 3x squared, we have a plus 6x minus 1. Notice the answer for G circle F is different than the F circle G answer was. Those are two different functions. And the reason, of course, is because we're inserting different functions into different ones. To do F circle G, we're putting G into F. To do the other way, we're putting F into G, and so it looks different. Now, this asks us to find F circle F. You can do a composition of a function with itself if you want to. Now here, notice F is on the outside, but F is also on the inside, isn't it? Now we replace the inside with first, so leave the F out here. F of x is x squared plus 2x, isn't it? Now this says look at function F again, right here, and replace our x's with x squared plus 2x. So that means I'm going to have x squared plus 2x here, which I square, and then plus 2 times x squared plus 2x again. Now look at that again. F of x is x squared plus 2x. Now this says find F and replace these x's in F. See, our x's here have been replaced with the x squared plus 2x thing. Okay? Now let's do some algebra. Let's square this. Okay? If I square x squared, I get x to the 4th. If I multiply these, I get 2x cubed. If I double that, I get a 4x cubed. And if I square this, I get a positive 4x squared. And then distributing, I have 2x squared plus 4x. And let's combine those like terms. X to the 4th plus 4x cubed plus 6x squared plus 4x. So there is F composed with itself. Okay? Now let's do one more. G circle G. Again, which function's on the outside? G is on the outside, but G is also on the inside. G of x. Replace on the inside first. G of, in place of G we put 3x minus 1. This says look again at function G and replace your x right here with 3x minus 1. So we have 3 times 3x minus 1, subtract 1, don't we? Distributing, 9x minus 3, subtract 1, and then simplifying 9x minus 4. Okay? So you see we got 4 different functions depending on which way we were doing the composition. Now notice the important thing here is the outside function stays on the outside. The inside function goes on the inside. Replace inside function first. Just replace it inside here, and then go to this outside function, and whatever you have here replaces the variables in that outside function. Okay? Now on our last example, we have three functions. We're to do the composition f circle g circle h. Okay, let's think about what we did before, and I think we can follow this through. F circle g circle h of x. Okay? Now, what's on the outside? F is on the inside. What's on the inside? G circle h of x. Okay? Now, I'm going to take this a little bit further. I'm going to leave this, f, and inside here, when I have g circle h of x, g is on the outside, h is on the inside. So really, when you say f circle g circle h of x, you're saying f of g of h of x. And notice that very inside function is the very inside function here. We're going to start on the inside and work our way out. Okay, so let's leave our f, our parenthesis, and our g, and we're going to replace h of x with what it's equal to. Well, h of x is the square root of x plus 2. Okay, so we've replaced the h of x. Now, this is on the inside, so we're going to work there next. Leave that f out here. This says in function g, replace x with this square root. So we're going to have the square root of x plus 2 squared minus 5 in there. Now before we go to f, let's do a little bit of simplifying on that inside part. What happens when you square this square root? It removes the square root and you have x plus 2. Bring down your minus 5. Now let's keep simplifying. What's x plus 2 minus 5? It's x minus 3, isn't it? Now we have it in a more simplified form that we know exactly what to do. We're looking at function f now, and we're replacing the x with x minus 3. So 2 times x minus 3 plus 1, and simplifying 2x minus 6 plus 1 gives us 2x minus 5. Now let's follow that again. F circle g circle h. F is on the outside. G circle h went inside, and then in here f, g, and then h went way on the inside. Okay, you start here, replace replace h, and then here go to g and replace in g this value. We did that here and simplified, and then go to function f and replace this into function f. Okay? Now, this might be a little bit more complicated, and you may want to spend some time there looking at that example. You may want to rewind your tape and look at it again, but be sure you understand how to substitute into these composition of functions. Now, the composition of functions is the more difficult of the operations because it's just so different than what you're used to. If you really have a good understanding of what that f of x notation means, however, you should be able to follow that and be able to do these compositions successfully. If you're having a lot of difficulty, you may want to go back and check out that first tape on functions where we worked a lot with that f of x notation and simply replacing things in for that argument of our function. This completes our lesson. I hope that you have gained valuable information from it. Thank you.